Okay, this is chapter 5.3, graphing radical functions. Functions, radical. Essential question, how can you identify the domain and range of a radical function? What you will learn, graph radical functions. You'll learn how to write transformations of radical functions and graph parabolas and circles. So let's take a look. Okay, before we get into examples, there's a graphing radical functions core concept. So a radical function contains a radical expression with the independent variable in the radicand. When the radical is a square root, the function is called a square root function. When the radical is a cube root, the function is called a cube root function. So core concepts say parent functions for square root and cube root functions. The parent function for the family of square root functions is f of x equals the square root of x. So as you can see the graph here, in order for it to be a function, it has to pass the vertical line test. In other words, you cannot have one x going to two different y values. So if I were to graph the square root of x and it was a positive or negative, it would also come down here and mirror across the x-axis, but then that would no longer be a function. It would be a relation, but not a function. So the parent function of the family of square root functions is f of x equals the square root of x. We're only going to graph the positive side. So the domain of x is all values greater than or equal to 0, and the range would also be greater than or equal to 0. So the x's and y's are both positive or 0, so we're in the first quadrant. The parent function for the family of cubed root functions is f of x equals the cube root of x. And when we graph that, it looks like this. And so therefore, this is a function, and the domain is all real numbers. And the range is also all real numbers because it does not map any x's to the same y. So there are the parents of square root and cube root of x. Okay, so here's example 1, graphing radical functions. All right, so to graph each function, we have to identify the domain and range of each function. So here is a square root of 1/4 x. Now remember, square roots can't be negative because if they are, they're imaginary. So I'm going to start with 0. So if I start with 0 here and I put it in this function for x, 1/4 times 0 is 0, and the square root of 0 is 0. Now, I'm not going to choose any values that'll give me fractions. So multiplying by multiples of 4 will get rid of fractions. 1/4 times 4 is 1. So if I put 4 in for x here, 1/4 times 4 is 1. The square root of 1 is 1. And then if I just go in multiples of 4, the next one would be 8. 1/4 times 8 is 2. The square root of 2 is, get my calculator and do square root 2, enter, and it's 1.4142. Okay, so that is going to be 1.41 rounded to 2 decimal places. The next multiple of 4 is 12. So 12 times 1/4 is 3. And the square root of 3, square root 3, enter, is 1.73. There it is. Okay, and then finally 16 is the next multiple of 4. 1/4 times 16 is 4. The square root of 4 is 2. So if I graph these points now, there's my table of values. I plot the point 0, 0, which is right here. And then I go over to 4 and up to 1, which is right here. And then I go over to 8 and I go to 1.4 something, which is just below 1.5, which is here, and then here's 2. And then if I go over to 12, I'm up to 1.73, which is almost 1.75, so it'd be about there. And then finally 16 brings me up to 2. So it's a really slow growing function. And actually this is 1.5, so this one's a little low. This is 1.5, not 1.75. So 1.73 would be more like here. So then when I draw my line, or my graph, this is a little difficult with this program. It's going to grow very slowly like so and go like that. So it's going to curve up and look something like that. Okay. So there is the graph of a square root function. Now looking at a parent function of g of x, remember if I go back, the parent function of a square root function is this. We can't plug in values less than 0, but this domain is negative infinity to infinity. So I'm going to plug any value in I want, positive or negative. So I'm going to start with negative, what was it, 2, I think. So if I put negative 2 in here, I can't find the cube root of negative 2, but then I need to multiply it by negative 3. So if I get my calculator, I can do it all in one step. So I just put in negative 3 and then math, and then the cube root is 4. So negative 3 times the cube root of negative 2, and I hit enter, I get 3.779 or 3.78. Okay, so I'm just going to leave this open for now. So the next value I'm going to choose is -1. So I'm going to pick just any value. So if I just hit second enter on my graphing calculator, all I have to do is change this 2 to a 1 and hit enter. And that is 3. So if I plugged in -1, the cube root of -1 is -1. -1 times a -3 is +3. I actually didn't need my calculator for that. Next one I will do is 0. Cube root of 0 is 0. 0 times -3 is simply 0. And the next value I'm going to choose is 1. And the cube root of 1 is 1 times -3 is -3. And then finally 2. If I put 2 in, I get the cube root of 2 times -3, which would be the negative of this, which is -3.78. Okay, so now when I go to graph this, I'm going to go to -2, and it's going to be 3.78, which is approximately there. Go to -1 and up to 3, which is right here. Go to 0, 0 is here. 1, -3 is here. And 2, -3.78. So here's here's 2, here's -2, here's -3, here's -3.5, -3.78 is approximately here. Okay, so now you can see this graph is coming down like so, coming down and then turning and going this way. So there is the graph of this cubic function. G of x equals -3 times the cube root of x, and this one is the square root of 1/4 x. And I probably should label these. I'm going to say f of x equals 1/4 x. And in this one, I would write g of x equals -3 times the cube root of x. Okay, so that's how you graph radical functions. So at this point, you should be able to do problem number 9 and 10 in the homework. Okay, so in example 1, notice that the graph of f is a horizontal stretch of the graph of the parent square root function. So let's take a look at that, what they mean by that. So here is the square root of 1/4 x. So if I were to graph the parent function, which is, let's call it h of x, just the square root of x, well, the square root of 0 is 0. The square root of 4 is 2. The square root of 9 is 3. The square root of 16 is 4. So this would curve up like so. I got 1 point out of place. I put the square root of 4 as 1. It's actually supposed to be here. Okay, so the square root of 4 is 2. So this is going to curve up just like this. So this parent function is growing slower, or this parent function in black would be here. The red one is growing slower because of this 1/4. So it says here, horizontal stretch of 1/4 is actually a shrink, or horizontal stretch is a vertical shrink. Okay. So now the graph of g of x is a vertical stretch. So if I go back, here is g of x. Now, if I call the parent function h of x, and that is just simply the cubed root of x, then the cube root of 0 is 0. The cube root of 1 is 1. The cube root of -1 is -1. The cube root of, let's see, next perfect cube, 8 is off the screen here. The cube root of 8 is 2. So 8 would be out here at 2, and -8 would be down here at -2. So this is going to curve and go like so. So this one is reflected and stretched. So as it says here, the graph of g is a vertical stretch and a reflection in the x-axis of the graph of the parent cube root function. You can transform graphs of radical functions in the same way you transformed graphs of functions previously. So the core concept for radical functions is basically the same as quadratics. So a horizontal translation graph shifts left or right is f of x minus h. So for example, g of x equals the square root of x minus 2 is a shift right 2. X square root of x plus 3 would be shifting left 3. Remember h and k. And vertical translation, square root of x plus 7 outside the radical shifts it up 7. And square root of x minus 1 outside would bring it down 1. A reflection in the y-axis is a negative under the radical in the function, and a flip over the x or y-axis would be the negative out in front. Horizontal stretch or shrink, graph stretches away from or shrinks towards the y-axis. That's f of a times x, so there's that value other than 1. So if the a is under the radical, it's a shrink by the reciprocal, 1/3. And so same goes for the 1/2. The reciprocal of 1/2 is a stretch of 2. If a is out in front, then it's a stretch by that factor. So 4 out front would be a stretch of 4. And a 1/5 out front is a shrink by a factor of 1/5. So all the rules apply to radicals that applied to what we've done in other functions to date. Okay, example 2 is transforming radical functions. It says to describe the transformation of f represented by g, then graph each function. So here is the parent function, f of x equals the square root of x. So now we have a g of x equals. So what's happened here? Well, we want to, it says to describe the transformation. So this is h, and this is k. So it's underneath. So h equals 3. Okay, it's x minus h, and k equals 4. So what does a 3 inside? That shifts it to the right 3, and 4 shifts it up 4. The k being, so there is the explanation. Okay, a horizontal translation 3 units to the right, and a vertical translation 4 units up. So if I graph the parent function of the square root of x, the square root of 0 is 0, the square root of 1 is 1, the square root of 4 is 2. So the parent is coming up like so. Oops, this is really difficult to do without looking at my hand. Okay, so curving up like so, I guess that'll work right there. That is f of x equals the square root of x. Okay, so now I'm going to take and translate this 3 units to the right and 4 units up. So 0 is going to go over to 3 and up to 4. So it's going to start right here. This point here is moved over 3 and up 4. The point at 1, 1 is going to be moved over 1, 2, 3 and up 1, 2, 3, 4, which is going to end up here. And finally, 4, 2 is going to be moved over 1, 2, 3 and up 4. So it's over here. So this function is coming up like so. So it's just taking this function here and shifting it over 3 and up 4. So there are the graphs of the two. So this is g of x. All right, so that's what we're going to do in the other one as well. So now I look and I see that I have f of x equal to the cubed root of x. That's our parent. And we're going to graph g of x, which is a translation of the parent. So let's graph the parent first in black. And the cubed root of 0 is 0. The cubed root of 1 is 1. The cubed root of, let's see, the next perfect cube is not 8. It's 8. Okay, so this thing grows really fast. So I'm just going to stop there. So it goes like so. And the cubed root of -1 is -1. And it's going to come down like this. So there is the parent function. It might be a bit more defined like so. And then this should probably come up like this. Okay, so probably something like that. Okay, and that is the parent function, f of x. Now I'm going to take it, and what happened here with the -8 underneath? Well, that is a equals -8, and it's inside. So a -8 inside is going to be, well, it's going to still go here, because the cube root of 0 is still 0, -8 times 0. But then the cube root of -8, and if I put this in as 1, the cube root of -8 times 1 is -8, and the cube root of -8 is -2. So if I go over to 1, I'm down at -2. So this function is going like so. And then if I go over here, if I put a -1 in for x, that's -8 times a -1, which is +8, and the cube root of 8 is, or the cube root of 8 is 2. So if I plugged in a -1, I would get 2. So this is going to curve up like this. So there is g of x. So that is a reflection over the x-axis and a vertical stretch of -8, or it's a shrink, horizontal shrink of 1/8, either way you look at it. Okay, it's inside, so I should say a horizontal. So it's a horizontal shrink of the reciprocal of -8, which is 1/8. Okay, so that's the graph of a parent and a transformation. You should now be able to do problems 19 and okay, so example 3 is writing transformations of radical functions, and we're going to be doing modeling with mathematics. But before I get into this, what this problem is talking about is how much gravitational pull each planet has, and that's a very common physics related problem. So I wanted to bring this in to just give you an idea, reviewing where the planets are in our solar system with respect to us. So Mercury is the closest to the sun, then Venus, then Earth. Earth is the third rock from the sun, Mars, Jupiter, and so on. Okay, so the inner planets are the first 4 out to Mars. So Earth is greater than Mars. So we're doing a problem that relates Mars to Earth. So if I highlight that, let's use this one. So Earth and Mars. So we're comparing Earth and Mars. So Earth is bigger than Mars, and Mars is further from the sun. So their orbits are different. So the orbits and the size of the Earth or the size of the planets determines the gravitational pull. Okay, so that is why they're different. All the planets are different distances from the sun, and all the planets obviously are different sizes. So therefore, their gravitational pull is not equal to what is on Earth. So if the gravitational pull is greater, you would weigh more on a different planet than you do on Earth. And if the gravitational pull is less, you'd weigh less than on Earth. Okay, so I just wanted to point that out, and that's what this problem is basically relating to. So we're given a function e of d, which equals 1/4 of the square root of d. So we have an a, outside of the radical. So that is a, let's go back. If A is outside, that is right here. It's a vertical stretch or shrink. So since it is less than 1, this is a vertical shrink of a quarter. Okay. And that is an approximation of the number of seconds it takes a dropped object to fall d feet on Earth. So E stands for Earth and D stands for dropping in feet. And then over here, it says the function m of d, dropping something on Mars, is equal to 1.6 times the Earth's drop. Approximates the number of seconds it takes a dropped object to fall d feet on Mars. Write a rule for m. And how long does it take to drop the object to fall 64, take a dropped object to fall 64 feet on Mars? So the first thing we want to do is multiply ED by 1.6 to write that rule for M, and then find M of 64. All right, so that's what we need to do. So first of all, we want to write M of D equals 1.6. We're given that 1.6 times, let me just put a bigger dot there, times Earth times D. So you're taking the Earth's equation and multiplying it by 1.6. So now all we're going to do is substitute. Since E times D is equal to 0.25 square root D, that is going to replace E of D here. So that means that I'm going to then write the M of D equals 1.6 times, and I'm substituting in times 0.25. So I'm going to multiply that by 0.25 square root D. So all I did was substitute in E of D. All I did is replace it with what it's equal to. So there it is. And then what's 1.6 times 0.25? So then I get my calculator and I take 1.6 times 0.25, enter, and I got 0.4. Okay, so that is going to equal 0.4 square root D. Okay, so there is our equation for M of D. So it says write a rule for M. There it is, M of D equals 0.4 square root D. And then it says how long does it take an object, how long does it take a dropped object to fall 64 feet on Mars? So this is the new Mars drop. So now I'm going to say M of 64 equals 0.4 square root of 64. All I do is substitute in for D, 64. So then M of 64 is going to equal 0.4. That looks like 0 times 4. 0.4. And the square root of 64 is plus or minus 8. But remember, distance can't be negative, so we're going to use the positive. So M of 64 equals 8 times 4 is 3.2. So I said distance can't be negative, but time can't be either. And D is how far we're dropping it. So that is, let's see, 64 feet. That's distance. It can't be negative. Okay, so we get 3.2. And that is what? How long does it take to drop? So number of seconds right there. It says it right there, approximate the number of seconds. So for something to drop 64 feet on Mars is 3.2 seconds. Make sure you use your unit of measurement. It's very important in the sciences. Okay, so there it is. We came up with an equation, a rule for M, and then we found M of 64. So now you should be able to do problem number 39. Okay, example 4, writing a transformed radical function. Let the graph of G be a horizontal shrink by a factor of 1/6. Don't worry about the followed by yet. Let's focus on one thing at a time. So I'm going to go back to our rules. Horizontal shrink, factor of 1/6. So if I go back to our rules here, here's horizontal shrink. And if there's a factor of shrink by a factor of 1/3 would put a 3 in front. So a factor of 1/6 would put the reciprocal 6 inside the radical function. Just remember the rules, but I just wanted to go back and show you that's where this comes from. Okay, so now let me switch to my pen. So what we're going to do first is say, well, let's call it h of x. So I'm going to say h of x equals f of 3, I'm sorry, not 3. In this case, it's a 6, f of 6x. Okay, so it's a 6 inside. So h of x is going to become the cubed root, because here's our parent function. F of x is the cubed root of x. So that'd be the cube root of 6x. Okay, so that is h of x. That's the first step. Then I'm going to switch back to my highlighter, followed by a translation 3 units to the left. Write a rule for g. So let me go back to my pen and I'll switch to blue. And now I'm going to say, well, g of x is going to be equal to h of, and 3 units to the left, that's our h, x minus h, x minus a negative 3 is x plus 3. So that's a 3 units to the left is x plus 3 in the parenthesis. Okay, so now that's going to become, g of x is now going to become this shifted 3 units to the right. So that is going to look like the cubed root of, and I'm going to take that 6x, and I'm going to just take the x portion of it and add 3 to it. So that is a horizontal shift to the right, followed by a horizontal shrink of 1/6. Okay, and now I'm going to distribute and simplify this. So g of x is going to equal the cubed root of 6 times x is 6x, positive times a positive is positive, 6 times 3, 18. So g of x is going to equal the cubed root of 6x plus 18. So there it is. So it says write a rule for g, and I just have. Now I'm going to check these in using Desmos just for a change. So let me get Desmos out here. Let's see, where is Desmos? Let me drag this over like so. And the first thing I'm going to put in is the parent function f of x equals the cubed root of x. Okay, so I'm just going to type here f of x equals, and I want the cubed root. How do I do cube root? That's 3 times the square root. Let's see, cubed root. How do I do cube roots on this thing? Let me look. Okay, so I can't do a cubed root by just showing the cubed root. I have to change it to a rational exponent. So that would be x to the power of 1/3. That is the cubed root of x. So there's our parent function. Hopefully you remember that from previous chapter. So there is the cubed root of x. Okay, so now let me go back. Where else? What else was I going to do? So that is the parent function. And now I'm going to do h of x, which is the cubed root of 6x. Go back to Desmos. I'm going to call it h of x. And that's going to equal the cubed root of 6x. Okay, and then I got to do power of 1 divided 3, enter. Okay, so the blue one is our transformation where a was 6 or 1/6. Okay, so that was the horizontal shrink. So a horizontal shrink looks like a vertical stretch. All right, so that's the blue one. So it is horizontally shrunk, the red one to the blue one. And then finally, we're going to shift that to the right 3. So now I'm going to put this in my calculator, which is g of x equals the cubed root of 6x plus 18. Okay, so whoops. Let me go to here. So now I'm going to call that g of x equals, and it's going to be 6x plus 18, close parentheses, And I'm going to do the cube root of, which is to the power of, whoops, 1 divide 3. Okay, and that's the green one. So the blue one is a vertical, it's a shrink, okay, horizontal shrink. The blue one from the red's the parent, and then shift the blue one to the left 3 gives us the green one. Okay, and so that is how we check our solutions using a graph. So at this point, you should be able to do problem number, where am I? 41 and 42 in the homework. Okay, graphing parabolas and circles. To graph parabolas and circles using a graphing calculator, first solve their equations for y to obtain radical functions, then graph the functions. So let me get my calculator, and it's right here. Turn it on, clear it. All right, so here we go. Graphing a parabola, horizontal axis of symmetry. Use a graphing calculator to graph 1/2 y squared equals x. So I cannot graph this because if I go into y equals, well, it's not y, it's 1/2 y squared. So I can't plug anything in. I can't just put x, that'd be a linear equation. So I need to solve this for y. So first thing I'm going to do is write 1/2 y squared equals x. Now I'm trying to get y by itself here. Okay, so in other words, I got to multiply both sides by 2. This will cancel the 2 and the 1/2, and I get y squared equals 2x. Okay, so y squared equals 2x, and then finally I have to take the square root of both sides, and I get the square root of y squared, which is y, and I get the plus or minus the square root of 2x. Now I have the plus or minus here because I can get negative values plugging in anything for x that's positive. Again, our domain is restricted by the square root. I can't put a negative in here, it's imaginary. -1 times 2 is the square root of -2, and that is I root 2, and I don't want imaginaries. So 0 times 2 is 0, plus or minus 0 is just 0, and so on. All right, so I do now have what I can plug in to the calculator. It's y equals. So the first thing I'm going to do is take this square root of 2x and hit enter. That's the positive one. So I have to enter this 2 ways. And then I have to say the negative square root of 2x to get the negative side as well. So then when I graph it, I hit zoom 6 for standard, and there it is, and there's the other half. All right, so if I did that in Desmos, though, I would not have to get it in radical form first, but that is defeating the purpose of why we're here and learning about radical functions. Okay, so if I put this, I'm just going to show you, if I put this in, it was 1/2 y squared equals x. I can actually do that. 1 divided by 2, 1/2 y squared equals x. Okay, and so Desmos does a really nice job of graphing stuff, even if you don't have it solved for a variable. There is the same graph I got with my graphing calculator, TI. Okay, a lot of people are like, well, why are we using a Texas Instrument then if Desmos is so much better? Well, when you go to take standardized tests, such as the SAT, the ACT, the ASVAB, any AP exams, when you get higher in math, they allow a TI-84 calculator on the test, on the calculator sections. You can't bring a computer and get online during a standardized test. Internet is banned. So how are you going to use Desmos without the internet? You're not. So you should be able to do this in a TI calculator. Yes, it's easier to see in Desmos, but Desmos is not allowed on tests. Okay, so there it is. We identify the vertex, it says. So identify the vertex. Well, the vertex is 0, 0. Okay, the vertex is 0, 0. So I'm going to write that. Vertex equals, no, it's not equals, it's not an equation. The vertex is the point 0, 0. And the direction the parabola opens, it opens to the right. Okay, so it opens to the right. So there is example 5. So at this point, you should be able to do, it's hidden behind me. Let me get it out of the way there. Problem numbers 51 and 52 on your homework. Okay, now we're going to get to example 6, which is graphing a circle centered at the origin. So use a graphing calculator to graph x squared plus y squared equals 16. So again, we're going to get this ready for the TI by solving for y. I want to get y by itself. So x squared plus y squared equals 16. The first thing I'm going to do is subtract x squared from both sides. So this is going to give me y squared equals, now I can write 16 minus x squared or negative x squared plus 16. I'm going to write it like this, 16 minus x squared. And then I'm going to take the square root of both sides. So then you take the square root of this and you take the square root of that. And I am going to then get y by itself equals plus or minus the square root of 16 minus x squared. So now I can plug that in my calculator. So I go to my calculator, turn it on, go to y equals clear, and go back up to y1. 1 is going to be the positive square root of 16 minus x squared. Whoops, not times. 16 minus x squared. And then I'm going to do the negative square root of 16 minus x squared. And I'm going to zoom 6 to center it. And there's half my circle and there's the other. It doesn't really look like a circle. So here's where you have to learn how to use this calculator. So if I press zoom now, there is a zoom command that's called zoom square. Where is it? Did I miss it? Zoom square. Oh, there it is, 5. Zoom square is 5. And that's going to just square it up and make it look more like a perfect circle. There it is. That just squares the screen, because think of this as the screen is wider than it is tall. So it's like a big screen TV. All they did was made this look square so that the distance left right is equal to the distance left down. Okay, so there it is. There is our circle centered at the origin. It says identify the radius and the intercepts. Okay, so I'm going to do this in Desmos as well. Where's my Desmos? Right here. And I'm going to do it the most simple way, which was the original. X squared plus y squared equals 16. So it's going to be x squared plus y squared equals 16. All right, so there it is. Same as my graph in the calculator here, but it's easier to see on this screen here. So here is a circle centered at the origin, and it says identify the radius and the intercepts. Well, the radius is the distance from the center to the edge. So the distance from 0 to 4 is 4. So the radius is 4, and the intercepts are 4, 0 and negative 4, 0. But there's also y-intercepts at 4 and negative 4. So now I'm going to answer all those questions. Okay, so the radius, now remember, the standard equation of a circle is x squared plus y squared equals r squared. Okay, if you don't remember that from geometry, then just looking at this without graphing it, the square root of r squared is r, right? So the square root of 16 is 4. So the radius equals 4. You can get that right from the graph. Just take the square root of what the x squared plus y squared is equal to. So r is 4. That's the radius. And x intercepts. There are 2. And it is over 4 up 0 and left 4 up 0. The y intercepts were over 0 up 4 and over 0 down 4. So the point 4, 0, negative 4, 0 are here and here. X intercepts, y intercept of 0, 4 and 0, negative 4. And so there's the answer to the questions, the radius of 4 and the intercepts. So at this point, you should be able to do the problems, which are 57 and 58 on the homework. Okay, this brings us to the end of chapter 5.3. And these are the exercises I assign my students. So please do your homework and thanks for watching. Have a great day.